Yeah, hello. Good morning, everybody who's listening and watching out there on this YouTube presentation. My name is Kai Steinbach and I'm responsible for the engineering department at the LZS. And I'm very proud and excited to be your host today inside this presentation in the Industry Days 2022. It seems to be not only the first time for the Industry Days to be an online event, but it's also our first online presentation on YouTube. So we, and especially I, would be very happy to hear your comments, your chat messages and your thoughts afterwards. And of course, in the end, if you place enough questions and remarks in the chat and the comment section, we will have surely some time after the presentation to answer and discuss your individual questions via this YouTube channel. So what we are going to do today is that I want to show you how we at the LZS use a very efficient design process and methodology to maximize your weight savings in the design process. And I prepared some slides for you. And the first point will be that I discuss and explain how we work and where's the difference to the traditional way of design processing. And then I prepared some, not some, but two examples about an optimized lattice structure for additive manufactured components and a composite antenna beam for a rail application. As already said, we are going to wrap up what we've heard today, and then in the end we surely have some time to discuss everything. So if I twitch my head a bit strange in the next minutes, it may be that I watch the comment section, which is on a screen aside me, so don't bother about that. It's not that I'm quite mad in the mind. So let's hop directly into the first step, how we work at the LZS. What you see here, and what most of you surely know, is the so-called complete design process chain. And it's of course an ideal model, but it should consist from 5 individual steps. So if it starts always with the feasibility study, goes then into a design and simulation process. Then you're going to manufacture some prototypes, and in the end you test it and validate what you had done on assumptions during the process. If some of you have the luck to see all these steps and with all your design projects, the whole process chain as shown here performed, you're quite lucky. But we all surely know examples where only individual process steps from these chains are used, and in the end you have often enough you see and hear of problems resulting from a not good interaction between those individual steps in the design process. So, and as the LZS is an independent, material and technology independent consulting company with the focus on lightweight design, we try to use this process and project structure a bit different. What we developed in the late years is how we call it the eye of the lightweight design. You see that all the steps we've discussed before are again here, but they are much more interlinked. And in the center of every lightweight design project, we think should be a really close interaction and an idea and knowledge transfer between simulation, design and testing. This means that you have really always the newest and best proven data available for your simulation, for your design, and you have the latest concepts and ideas from the design available for your testing. Of course, This close interaction will only be successful if you had in the beginning of such a project done a quite detailed and thoroughly prepared feasibility study. So it often enough happens that even in the first steps of the feasibility, you use some ideas from the design department, or you do your first simulations, or even, and also this link can be drawn from this sketch, you do first testing, because you have a new material, you do know how it behaves, and this is something you should know already in the feasibility study. And of course, you have a close interaction with the manufacturing department. In the case of the LZS, it is mostly prototype manufacturing. But if you plan for a larger serial manufacturing, then of course you're gonna have to discuss everything regarding simulation, design, and feasibility from the beginning with your manufacturing department. Because the best idea from the design is not worth thinking about in the second your technology guy on the shop floor tells you, no, that's not possible. Because we do not have the machines, we do not have the tool technology and all the other stuff we see in real life. So that's how we try to do our projects, and as we increase the use of this development scheme in the late years, we became more and more successful and reduced the number of projects where you had a point of early project failure because you just forgot someone to ask. So that's from the beginning for the first steps. And so now let's hop into the examples. The first example will be an optimized lattice structure. Here I want to go a step aside from the real work we've done and to start with some thoughts about composites. The main idea of composites is to combine some mechanical, quite performant material, mostly the fibers, with some material which has the main task to just hold the other one together. And if you think this quite further on and to the extreme point, you will end in a classic framework design like we know from years and centuries ago. And you can find it with steel, you can find it with wood, you can find it with all materials where you combine a quite strong material with a soft material, means air. So you just leave the metrics away. That's from the basic idea, the idea of composites driven to the max. And today, frameworks or their three-dimensional relatives, their lattice structures, have some kind of revival. And this is coming from the additive manufacturing technology. In the additive manufacturing technology, you have 2 points. The first point is that with these technologies, it's quite easy to manufacture even the most complex lattice or grid structures. And the other point is you need these lattice and grid structures for supporting your material if you want to manufacture some hollow components. And this hollow component or this need for grid structures led in the LZS to the idea to use the lattice or grid structures as mechanical elements in the design of components. This idea is quite new because normally these structures are only used as technology helpers, just to improve your printing or your 3D manufacturing process. And so the idea was, how can we use these letters and grid structures as mechanical parts in the design. And the problem is, as I showed in the beginning with this lightweight design eye, to use something as a mechanical element in the design, it means you need to know the mechanical properties for a good simulation and a good mechanical design process. The trouble 3D printing and additive manufacturing gives you is that it's a primary forging process, and the material itself it generates has a really strong influence of the process. So it's quite complicated to identify your real material properties, because it's not only depending on the process parameters itself, but it also is depending on the position in the material and even in the positioning of the part inside your technology space. You can see this on this sketch here, where you have this individual specimen printed in different directions, and the result from this is that you have, for all the different directions, you see different mechanical behaviors. And in the end, especially the powder-based materials show quite low overall property levels compared to the bulk material. That's understandable, but you have to take care for it. And right now, you do not have a closed development chain or a simulation tool where you can just put in your parameters and get the results from that. So the idea is we need a reliable simulation process to understand the 3D printing before we can use the grid structures as structural elements. And as we have a quite strong simulation department, we started working together with a partner here in Dresden, the IFW from the Leibniz company. And the first thing a simulation guy always does is to design a parametric unit cell model. So this means we modeled such a unit cell for a lattice cube, and because it's so small and it has not many design features, you can modify it quite easily and can test a lot of different geometries and can model easily quite strange grid densities, grid structures, grid components. And when you fill some validated bulk material properties into this model, you can do some simulations, and you get the mechanical basic behavior of such a grid unit cell. And of course you can look where it's heavily loaded, where it will gonna fail, and you can identify what's an optimized design of such a grid depending on your load conditions. And of course we made use a bit of our experience that composites and fiber reinforced polymers have also a strongly orientation dependent property scheme. And with that parametric unit cell, we were able to build up our own grid structure and material database. So after this step, we had understood how such grid structure works in the microscale and what would be the best geometry and density. But as I already said, especially those powder-based additive manufacturing technologies are quite sensitive regarding the process behavior. And what you see here is an CT scan of a real additive manufactured grid structure. And especially in the powder-based technologies, you have two problems. The first problem is voids, so it means you have small air gaps between your metal powder, and during the melting by laser or other technologies, these voids do not go away. You still have gaps in your materials. And we all know that from a mechanical point of view, it's not only that where there's a void, there's no material, it's also some kind of notch effect, so it decreases your strength in two different ways. And the other effect you have in the powder-based technologies is the so-called sintering artifacts. This just results from that when you melt your material with your laser, it's still, even if you have the fastest heat and cooling rates available on the market, the material is still a bit longer hot than you needed, and some powder laying aside or beneath your focus point will get melted and stick to the material itself. So you see also from these images that the influence from the process is quite severe, and basically it's no prediction possible. So in theory, someone may run a 10 years research project and simulate something like this, but in the moment there's no way to predict this behavior and the influence on the overall strength of such a grid. So here testing is inevitable. And this we did. So together with our partner from the IFW, we manufactured such grid structures and tested them in different loading conditions. Of course, we did not do all of available load combinations. We did a bit of design of experiments to reduce the amount of tests to be done. And with these test results and also some three-dimensional measuring during the testing, we are now able to calibrate our material models and our parametric unit cells to calibrate the influence of the process and the real material behavior into our simulation models. And in the end, from that, if you have proven your material model and validated it, you can derive a representative volume element and have now the option to use really validated RVEs in a larger scale simulation. And this we did. Here we designed a bracket structure. The bracket structure was planned to use as a load introduction feature for a hydrogen tank. And when you do some kind of topology optimization, you will end up in such a biological or bionic shape. And the good thing with additive manufacturing is that these shapes are the first time manufacturable and even as a hollow structure, as you can see here. But as discussed before, this hollow structure must be filled with a grid. And of course, it's not possible to fill such a structure with a grid model and do then an optimization, but with our now available RVEs, we can combine a normal topology optimization system with our RVEs and are now able to run an optimization of the whole structure consisting of the monolithic shell and the grid structure within. And in the end, this really helped us along on this project, because when you leave the lattice structure away in the simulation, you will see, due to the loading conditions of this part, that you have, as you see on these red marks here, that you have a quite high shell loading, which will lead to local instability. And if you now increase the density in your areas with the high shell loading, you can avoid the local instabilities in the shells, and from that on you can reduce the thickness of your shell to the amount that it's needed from the strength perspective, and you will in the end increase your ultimate loss, because you just avoid the local instabilities. In that case here, the ultimate load was increased by the factor of 3, so that's really a lot, and it ends up in the maximum weight saving for this project. And here you see we in the end also did the real life test. We did 3D printing together with the IFW, and had now this structural loaded bracket. We could use a standard SLM material, could use this topology optimized geometry, and inside we had our optimized lattice structure with locally varying densities and strength, and have now available the complete simulation and development chain for the optimization of such lattice-filled 3D printed structures, which is quite a huge step forward on the way to use only the minimum weight of material. And you can surely imagine that if you leave, especially in the 3D printing, a lot of material away, you do not need it during your technology, you save a lot of time, and not only the material itself. So you have a 2-point bonus on that. You're saving material and you're saving manufacturing time, which are both critical points in the additive manufacturing, actually, in the serial manufacturing. Okay. Can this procedure used somewhere beyond lattice structures? Of course. You can imagine that this process, coming from a parametric Unix cell over validated and calibrated material behavior to an RVE, can be used for almost all applications where you have an inner detailed structure. One example I have prepared here is the optimization of honeycombs and sandwich materials. And if you have one geometry and one material behavior calibrated, you can then, with some supporting tests, step into the so-called virtual characterization. So you run just theoretical calculations, how different geometries, how different materials will behave. And in the end, if needed, you can derive from that such carpet plots, and your engineers in the design department can easily identify which will be the best configuration, for instance, for your honeycomb. And of course, if you have this RVE completely calibrated available, then you will also have the option to use it in an optimization tool, and then may end in sandwich structures with locally different honeycomb designs or properties. Okay, that's so far for the optimized lattice structure. Now to the next example of the composite antenna beam. The composite antenna beam was a project together with Bombardier, and it's from a completely different application than the bracket and the lattice structure. It's an antenna beam which does what its name called for. It holds some antennas and it's located on the bogie of a rail engine, and its main task is to position these antennas directly above the tracks and to get electronic signals from some sensors and to identify obstacles. And you can imagine that this antenna beam is quite important for the quality of this data acquisition, because if this sensor beam has a bad mechanical behavior, so too low eigenfrequencies, too heavy, too soft, in the meaning that it breaks often, it gives you really headaches, because we all know that actual trains are quite heavily loaded with electronics. If one sensor like this antenna fails, you may end up somewhere in the nowhere with your train stuck, and you may have a problem. So the number of units per year is comparably low, but not that low that it was not worth to think about a composite solution. But there's one major headache we see here, and this is the impact protection. You can imagine, as this is the very front end of a train, you always have to consider that some stones, some wood chips, even parts of trees, maybe even animals are laying around, and then the train hits it with roughly 40 meters per second or 120 kilometers an hour. And of course, these events shall not be critical to the part. It may be defect or it may break at such an event, but it shall not break catastrophic. So here again, we started really early with the combination of simulation, design and manufacturing in that case. Already in the feasibility study, we worked quite hard to understand the system itself, its task it has to fulfill, and especially what are the needs of the customer. To be honest, understanding the customer is sometimes, especially in the feasibility studies, the major issue, because such industries like the rail industry or paper machine industry or other industries like the chemical industry, they all have their individual mindsets, and to design a good and perfect part for their needs and their requirements, you really have to understand how they are thinking. And already in that early stages, we here started to compare different design options. So you can see we had like we called it differential design, which was more or less made from standard components. We had the so-called integral design, where everything is in one piece. And we had some, let's say, a mixed design, where you have an integral part and the functional elements connected to it in a differential way. And to differentiate between these individual designs or concepts, it's really necessary to interact heavily between your manufacturing partners and your simulation guys, because in the early stages of such a feasibility study, it's always good to do your decisions on facts, your information from your manufacturer, and also from the simulation guys who tell you what's possible and what's not possible regarding strength and stiffness of the material. And of course, if you have done a good first glimpse of simulation, you have available all or a good educated guess of the amount of material you need, and with the information from the manufacturing department, you will have all in hand which you need for a good cost estimation. And a cost estimation is the final part of each feasibility study, because we all know that in the end the costs will decide whether a project is running further on or not. After we had in this feasibility study decided for an concept to go on, the so-called preferred solutions, you see here. You see also that we decided for another option. We have a semi-integral main part, and we did the major challenge for the mechanical loads, the impact. We moved outside of the scope and said, okay, we have in front of the antenna beam, we will have some kind of impact protection sheet. And with that done, we could go into a technology-specific design, we could run the final material selection, and we could do the detailed 3D drawing and design. And of course, did then some market research with manufacturers, with material suppliers, and so on. In this phase, we did more detailed simulation and tried to understand all the effects coming now on top, not only the design, but also the material behavior depending on the manufacturing process. So we included all the technology related effects like local differentiating fiber volume content, like draping effects, like fiber orientation limitation, etc., etc. And did in that stage the final design optimization, and of course could, especially in the interface areas, could do some kind of global local interaction simulation to really identify the hotspots regarding strength on the part. In the end, we did some prototyping here, which is fitting quite good to the planned serial number. We used vacuum infusion technologies. Here we are quite free. We can do it in-house, or we are using one of our partners from the networks. And what we try to always to do, if it's not an airplane, we already tried to do the prototyping in real size and in the final technology. Because only in that way you can early identify your design hiccups, you can identify the best tool design, and you can already in the prototyping phase establish an idea how to ensure your quality during serial manufacturing. And if done right, of course, you have already after the prototyping available all your critical parameters for the manufacturing. So in best case, you have a set of parameters, you have your layout plans, you have your tool design, and can directly from the prototyping mode start with the serial manufacturing. In the end, you will not avoid it, but it's necessary to do some testing. Here are some examples about the impact testing procedures we did. Of course, this heavily depends on the wishes of your customer. If you want to do a classic testing, let's say more or less based on the mechanical properties, if you want to do a special non-destructive testing scheme, or if you go for a customer-specific testing scheme. Ideally, this proves that your design assumptions have been completely right. Normally, with our way of doing design projects, this is also the case, because if you really had a close interaction and communication between your partners and have included them early in the feasibility study, you shall at this phase not end with the idea that something has completely gone wrong. And of course, in that phase, you can also discuss the effects of defects, and you see how some manufacturing variation will result in your overall performance. Yeah, the result from that project were quite good. We had in the end part which is looking now like a real composite antenna beam, not only like a metal black metal design. We had the approval of the customer that we were fulfilling all its requirements. We reduced the antenna misalignment significantly. We had the weight down to 13 kilograms, which is almost a fifth only of the steel design. We are using only proven technologies like the vacuum infusion, and actually we are running this part, or the customer runs this part in fatigue testing for a whole life cycle of a bogie. And but we are quite confident that in the end we will have a proven design. Okay, so these are my two examples, and let's come to the conclusion. So what I wanted to show you today is that if you ensure a close interaction of feasibility study, simulation, design, testing, and manufacturing, you have a good chance to run really good lightweight design processes. Important point is your feasibility study must be based on the real requirements. It's a really bad idea to come somewhere along the simulation of the final bits and pieces to say, no, okay, we have found this requirement we forgot all the time. So this is really important. You have to understand the material and the process and how they have an effect on each other. The simulation in the end will be your key element in the design process, because only in that way, by using heavily the simulation, you will ensure that that your weight savings are maximized. You have to be aware that you must always ask your customer questions which may not be fun, but you have to ensure that your development is really unbiased of traditions, of these sayings that has never worked, we never done this, and all the stuff you know surely from your own projects. And you have, in the best way, run a complete development chain, but not as seen in the beginning as a chain, but as a close interaction of the individual points. So I'm gonna let this stand here for a moment, and that's what I wanted to show you today. I'm gonna be here for the next few minutes to wait for your comments, and please feel free to comment and ask me something. In the moment I see that there's not that much on the comment section and the chat section, so maybe that's the first time for all of us. And yeah, it was quite fun. I think that's a good way to run such an online presentation in this time, and I hope it made you as much fun as for me. If you see this video later on, because we will leave it on the YouTube channel, you can rerun it anytime. Just get in contact with us and just drop us an email, or you'll find us on our website, which is www.lzs-dd.de. So there you find all our contact details. Just drop us an email and we will come back to you for starting projects together with you. So as I see here, there's not much going on in the chat. I think we can leave the day for it, and I hope you will have a nice day, and I say bye-bye and meet you the next time. I'm quite sure that the LZS will go on with this kind of live streaming event, because it's really making a lot of fun. Have a nice day. Bye.